So what happens is in a black body, all energies are absorbed. All energies here are absorbed. So what that means is, what's going to happen is that this is going to fall back down. When this falls back down, energy's lost. So there's got to be some kind of energy input here. So we'll just say energy in. Energy's coming in from the surroundings here. All right, and so when this drops back down, then what's going to happen is, we're going to get some green, looks like green light is going to be emitted. And so we'll see green here. So we could shine, all the colors of the rainbow, like white light on this. If we shine white light on this piece of matter, it absorbs all colors. And eventually, it will also emit all colors of rainbow. We don't have to shine light. The energy in can be just kinetic energy, excites the electron, etc. That is heat. There are different ways to excite the electrons, electricity, other ways. And so this is a black body in terms of an absorber, and then it's a black body emitter. A black body emitter, what colors of the... Does it emit black light? A black body emitter, does it emit black light? No. Black body emitters do not emit black light. Black body emitters would emit white light, right? Eventually. Black body emitters, you have to put enough energy, because if you only have enough energy to get IR, then the black body emitter, like a piece of metal, is just going to emit heat. You can't see it, but you can feel it, And so if I take a piece of metal, metals are black bodies, put it in here, and it's going to warm up in the flame, but it's not necessarily going to be visible light, but you can feel the infrared coming off here, let's say. And so you excite a little bit. And then eventually what's going to happen to the metal? I think I showed this the other day. What's going to happen to the metal is it's going to start to glow red. It's going to get red hot. And so what's happening here is you're starting to emit some infrared and some red from that, correct? And then eventually, if you keep heating it, it's going to get hotter and hotter until it turns into, what? Did I show this? I think I showed this last time. So if we just heat a piece of metal, leave this metal doesn't burn. Do you see it's starting to glow orange? That's emission. So I'll heat it. Right now it's just emitting infrared. I don't want to touch this. We will burn my fingers. But now, do you see it's glowing? It's glowing red hot. But if I continue heating it, it's going to start glowing orange, and then eventually it'll glow, it'll glow more and more white. Once I start emitting all these, I'm going to get white light if it gets hot enough. We'll probably might melt. Let's see, it might melt. Let's see if I could get just the tip of this glow brighter. And so essentially this is a black body emitter here, because eventually I'll get all colors of light. So that just means, metals have what we call a sea of electrons. Those electrons are easy to excite, right? These electrons get excited. It's orange here. And eventually they'll drop back down, emit. And then violet, we're getting excited more and more. So if I continue adding more energy, eventually this should excite the electrons past the visible into the what? Into the UV. So, take a look. This. So this is getting hotter and hotter here. What we're looking at the intensity of the emission. So we see a band here. This band's pretty wide. Where's visible light from? Visible light ranges from what to what? Yeah, so here, 390 is around 400, let's say, around here, to 760 here. Past 760 is what we call what? Infrared, and below 390 is UV. And so we start heating this up. This is a 5,000 Kelvin. We start heating up the electrons. And the electrons are getting excited, and we excite them to different levels. So this is already emitting, rainbow colors. If we heat this, continue heating this up, we'll emit higher and higher energies of light, down to 390. We'll start emitting some UV. And as we continue heating this, we should emit more and more UV. But what happens is there's a precipitous drop here in UV emission. This classical theory just predicts that we should just follow this trajectory in terms of emission and temperature. Temperature is just exciting the electrons. And so we see this. So basically what's happening here is it's not behaving as expected, because a black body should absorb and emit all energies with radiation up into the UV, up into the X-ray, etc. Well, this is called the This is called the UV catastrophe. It wasn't behaving as expected. And to fit this mathematically, they had to do something with the light. This is what they had to do with the light. The light, energy and light is a little bit tricky because we have some terms and they get confused. To explain or to fit, this, or to describe this UV catastrophe, what had to be proposed is this, that light comes in little packets. And so basically there's a continuum. This is what we call a continuum here. There's a continuum of energies, from infrared to UV, continuum of energies. But when we look at the light itself, let's pick one, wavelength of light. Let's pick a wavelength of light here. A wavelength of light here, the light comes in little packets, like this. These little packets are called photons of energy, photons. And that's just a packet of light. So in a way, light is continuous, but it's discontinuous. It's continuous in that, are there any colors of the rainbow that are missing? Are there, when you look at the white light and break it into its spectrum, there are no gaps. All the colors of the rainbow are present there. And so it's continuous in one way, but it's discontinuous in another way. That is, if you pick a specific color and look at that light is discontinuous in the sense that the light comes in packets called photons. And this is similar to matter. If you had some sugar, can you weigh out any amount of sugar you want? And the answer is no, you can't weigh out any amount of sugar. the amount of sugar you can weigh out has to be, n, where n is some integer multiple of a sugar molecule. And so let's say if you tried to weigh out, like, let's say sugar weighs glucose. Let me take an example here. Glucose weighs 180.2 U. It's a single molecule of glucose. And so if I tried to weigh out, I want 190 U worth of sugar. Is that possible to weigh out 190 U worth of sugar? No. Because the next amount of sugar I can weigh out will be double this. It will be 360.4 U. Actually, we have to account for isotopes, which I'm not doing. I'm just taking the average here. But just to illustrate a point, I'm going to jump here. And so in this sense that, mass is discontinuous. Mass is discontinuous because I cannot weigh out any amount of mass I want. I have to weigh out, n times whatever the smallest packet of mass is. And the smallest packet of mass depends on what the substance is. So, for example, water, I can't weigh out any amount of water I want. The amount of water I can weigh out is n times the mass of a single water molecule. Yeah. Well, it turns out light is the same way. Let's say I pick at 760 nanometers. At 760 nanometers, then light is going to come in little packets like this, so I can't get any amount of light I want. I could get 1 photon, I could get 2 photons, 3 photons, I can get n times the number of photons, but I can't get a half a photon. It's not possible. Or 1.5 photons. And so what that means is this red light is discontinuous in a sense. Discontinuous means, we have another name for discontinuous. Discontinuous. We call it quantized. So light, like matter, is quantized. It comes in packets. So continuous means I can have any color, but once I pick a color, then I look at it and the light turns out to be quantized. Well, this has an impact on energy, so I'll talk about that next. If I compare that to 390 nanometers, let's go to 390 nanometers. Violet light at the end of 390 nanometers is also quantized. The difference is the size of the energy packet. Red light has a small energy packet, but violet light has a much larger energy packet. And so violet light has just bigger chunks of light, I guess you could say. In that sense. Well, if you take into account this quantized nature of light, then what happens is you could fit these mathematically to observation. And so what they had to do is they had to modify this, that light comes in little packets called photons. Once you do that, then you can see it. Now the size of the packets varies continuously. So if I'm at 760.3 nanometers, the packet's a little bit bigger. 760.33 nanometers is a little bit bigger. And so the packet size varies continuously from very small packets, red, to very large packets of violet. We have a continuous increase in size of the packet. And so, again, it's a continuum here, but it's discontinuous here, or quantized here. Well, that has an impact on energy, and this is seen in the photoelectric effect. Well, first off, this discontinuous or quantized, this packets of light, this fits the UV catastrophe. It's called the UV catastrophe because physics at the time, which we call classical physics, wasn't able to describe black body emission until the proposal here, Max Planck. Energy like matter is discontinuous. And so the size of the packet, this is the energy of a photon, is equal to h nu. So the size of the packet, which is just the energy of the photon, is equal to h nu. And so we can't have any energy of red light. We have to have different packets. And so what are the packets? And so photoelectric, let's take a look at the energy. When we think about energy of light, there are two ways we look at the energy. One way is the total energy. Total energy is going to be related to the amplitude of light, or intensity of light. Amplitude, let me tell you what amplitude is. You know, okay, this would be, lower amplitude is just the height of the peak here. This would be the amplitude. And so, bigger wave like this have a higher amplitude. A higher amplitude is more energy. This is a higher energy. This would be like a tidal wave. This would be a small wave here. And so the greater the amplitude, the increase in the amplitude, the increase in energy. But, you know, we have to be careful because this is the total energy. But we also have to think in terms of the other energy. And that would be the photon energy. So, in terms of the photon energy, a low amplitude wave like this, when we look at the photons, these are photons, there aren't that many photons compared to a higher amplitude wave, this. A higher amplitude wave would have a lot more photons. So this has interesting implications. For this. This is Einstein. Einstein won the Nobel Prize for the photoelectric effect. But the photoelectric effect is this. You shine light on a piece of metal, and if the light has enough energy, it can ionize the metal. You know? If the light has enough energy, ionize the metal. So, let's look at something like a 5-watt light bulb. 5 watt. A watt, do you know what a watt is? A watt is a joule per second worth of energy. Joule per second. Watt is. And so this would be 5 joules of energy per second. 5 watts. And so let's look at some blue light. If I do 5 watts of blue light, this strikes the surface of this metal is going to be like a potassium solid. Potassium solid has to be protected, so that's why you see the chamber there. It says evacuated chamber. Because if there's air in this chamber, then what's going to happen to the potassium is it will be oxidized. So to keep the potassium as a metal, we have to make sure we take out any air in this chamber and moisture, humidity. Water will attack potassium metal too. And so when the blue light hits this, then what happens is an electron gets ejected off the surface. And the electron, if you have a detector there, you see the electron is going to be accelerated to the top plate there because what they do is they place a voltage. What a voltage is they just put a charge on the plate. So electron's negatively charged, and that top plate up there is positively charged. And so the electron's going to be accelerated up to that the top plate. But before it gets to the top plate, it's going to hit that grid, I think. Or maybe it doesn't. No, it doesn't hit the grid. It passes by the grid. The grid is what accelerates it, sorry. And then it hits that top plate where you measure a click. And so what happens is this. If the light is hitting this, we get what's called a current, a continuous current. That is, electrons flow, making electricity. If the light is blocked, then the electrons stop flowing, right? And then a little bell goes off, bing. You know? And so these are these photoelectric detectors that they use for many different purposes. Well, let's say 5-watt blue light bulb is fine. Okay. So what if I go, okay, now I'm going to try red light. And I'm going to do this. I'm going to go, let's go 5 watts of red light. If I go 5 watts of red light, nothing happens. 5 watts of red, well, that's 5 joules per second. It's the same energy. 5 watts. Nothing happens. Well, nothing happened there, but I'm going to go, okay, if nothing happens there, let's bump it up. I'm going to go to 100 watts. Surely with 100 watts, 100 joules per second, something should happen. But nothing happens. Nothing happens, well, it's going to warm up. The metal gets warm. Let's go to 1,000 watts. 1,000 joules per second. 1,000 joules per second is a lot of energy. Right? 200 times more energy. And so this is like this huge tidal wave of photons coming in. Tidal wave of photons coming in. And the 5 watts is just a little tiny wave, blue light coming in. So I got this tidal wave of photons. If I got a tidal wave of photons, surely I should be able to ionize potassium. But 1,000 watts, does anything happen? Nothing happens. It's going to get very hot. I'll probably melt this stuff, but no electrons get ejected. 5,000 watts. You think that'll do it? Make the gigantic tidal wave of photons. And it doesn't do it. It doesn't do it because the photoelectric effect is like this. Red light comes in little packets of energy, and these packets of energy are, the analogy would be something like a ping pong ball. And so if you have 5 watts worth of ping pong balls, so you got a lot of ping pong balls. 1,000 watts, you got a lot more ping pong balls. And so you got this enormous tidal wave of ping pong balls. But are the ping pong balls going to do anything to the surface of potassium? No, because the ping pong balls themselves, individually, do they have enough energy to knock an electron off? No. I mean, if you got hit with one ping pong ball, is it going to cause much damage to yourself? No. If you got hit by, 1,000 ping pong balls, will it cause that much damage? No. 1,000,000 ping pong balls? No. And so the blue light, though, the blue light comes in larger energy packets. A larger energy packet would be like a bullet, and so, 5 watts of ping pong balls is a huge amount of ping pong balls, but 5 watts of bullets isn't that many, like one bullet, let's say. One bullet comes in here and knocks an electron off. And so if I bump this up to 100 watts, what's going to happen? I'm going to have a tidal wave of bullets come in here. A tidal wave of bullets is going to knock a lot of electrons off, right? And so this is the two ways of thinking. In classical physics, which is traditional Newton's physics, they only think of energy in terms of amplitude. That's it. But in this new, what we call quantum physics, because the energy is quantized like this, it's discontinuous. In this new quantum physics, we have to take into account not just the total energy, that is the amplitude of the wave, but we have to think about what this consists of. And so when we think of large amplitude, we've got a lot of photons. Small amplitude, we've got a few photons. But the photons, the size of the photons themselves, will depend on the frequency or the wavelength of the light. And so let's take a look at these energies here. And so let's take a look at the range and energies here. And so let's get the smallest. That is, when I talk about the smallest, the lowest energy photon of red light would be at 760. There's a whole bunch of red lights, though. This would be at the limit here, 760 nanometers. And then red varies, And then at the edge of violet, we're at 390 nanometers. This would be violet here. And so what we're going to do is we're going to calculate, what is the energy of a red photon here. And so the energy of the photon is equal to h mu, or hc over lambda, where nu is equal to c over lambda. H is what we call Planck's constant. Planck's constant is 6.626 times 10 to the minus 34 joules times second. A joule times second is what we call a unit of action. Joule times second, so it's an odd unit. Joule per second is what we call a watt. Joule times second is action. Well, why don't you calculate the energy of this photon for me, and then calculate the energy of a violet photon for me. Okay. And then let's compare the two.